In theory, quantum mechanics runs backward and forward in time perfectly. The equations ignore the clock's direction until a stable physical record is left behind. If you look at standard state evolution, like the famous Schrödinger equation, it describes a closed, smooth loop. A particle's probabilities evolve in perfect symmetrical harmony, fully capable of rewinding back to their starting state without losing a single drop of information. But bring a detector into the lab, and that reversible tape suddenly stops. A measurement forces an outcome, creating an irreversible physical fact. Since we cannot rewind a tripped sensor, we have to find exactly where the pristine math meets the physical world. A theoretical framework called FDSQ0 proposes that the math remains intact, but the information simply crosses a physical boundary. Physical distinctions, like a particle being measured as spin up or spin down, exist relative to boundaries. Moving that distinction out of the quantum system and into a macroscopic apparatus or an observer's memory requires effort. It must be recorded, erased, or recovered differently across the boundaries of systems, apparatuses, and observers. Perfect reversibility exists as a highly restricted special case, occurring only when we successfully isolate a system from its environment. To measure this boundary crossing, Q0 introduces something called boundary access holonomy. Think of a physical process as trying to close a circuit through a system, an apparatus, an environment, and a recovery channel. Holonomy is the operational obstruction encountered when trying to close that loop. When the mathematical value of that holonomy, represented as h partial, is exactly 0, the system remains in the reversible, record-neutral quantum sector. The loop closes perfectly. No data escapes. A non-zero holonomy signifies that the loop has broken. Information has leaked out to form a record or cause decoherence, and reversing the process now requires a thermodynamic cost. We can see this in a Mach-Zehnder interferometer. We shoot a single photon down a path that splits in two, then recombines. Without a detector, the photon travels both paths, shifts its quantum phase, and emerges fully intact. It leaves no record behind. This is coherent holonomy. The loop stays closed. Now place a physical detector on one of those paths. The moment it clicks, the environment absorbs the which path information. The wave interference vanishes, and the reversible loop is permanently broken. We have entered record holonomy. This framework distinguishes between mere entanglement and the formation of a record. While entanglement involves the environment, a measurement requires the result to be stabilized as a physical record within an observer's finite register. Observing a quantum system physically breaks its reversible loop by permanently extracting a stable record into the macroscopic environment. We fight these broken loops in quantum computing. Quantum error correction is an active attempt to force these fragile quantum loops to stay closed against the constant pull of the outside world. This diagram maps out quantum error correction as a finite distinction maintenance ledger. Keeping a logical qubit stable requires an active, continuous accounting process that relies on physical work. Notice the specific flow. We go from noise and leakage into syndrome extraction, where we pull out error data, then feed down into the heat and cooling ledger. Maintaining a logical distinction in a noisy universe has a literal thermodynamic cost. We must pump heat out of the system to keep the quantum state pristine. But sometimes this maintenance fails.
This introduces leakage holonomy, the specific error where logical information escapes into uncorrectable environmental channels, completely bypassing the error correction hardware. Logical quantum failure occurs when boundary records leak outside our recoverable zone, permanently breaking the loop. These leaking records suggest that standard quantum mechanics describes the specific physical condition where zero information leaks past the system boundary. In FDSQ0, this is formally called the zero-holonomy quotient. If you take the messy, directed reality of boundary access and factor out all the stable asymmetric records, the symmetry that remains is exactly what we call standard quantum mechanics. This framework has strict limits. It does not solve the entire quantum measurement problem on its own. It doesn't derive the Born rule from scratch, and it doesn't replace standard quantum field theory. Its actual scientific purpose is to provide an upstream architecture, explaining why a symmetric, reversible quantum sector exists in the first place, rather than accepting it as an unexplained mathematical given. Symmetric reversibility appears as the pristine mathematical state left behind when every single record-producing boundary loop is successfully closed.